Hi, I'm Mohan, Assistant Professor, ECE Department, Government College of Engineering, CD, Tanjavur. We are going to discuss in robotics subject the Lagrangian formulation of robot dynamics. In the Newton-Euler formulation, the equation of motion are derived from Newton's second law, which relates force and momentum as well as torque and angular momentum. The resulting equation involves constraint forces which must be eliminated in order to obtain closed form dynamic equation. In the Newton-Euler formulation, the equations are not expressed in terms of independent variable and do not include input joint torque explicitly. Arithmetic operations are needed to derive the closed form of dynamic equations. So, an alternative to the Newton-Euler formulation of manipulated dynamics is the Lagrangian formulation, which describes the behavior of a dynamic system in terms of work and energy stored in the system rather than force and momentum of the individual members involved. The constraint forces involved in the systems are automatically eliminated in the formulation of Lagrangian dynamic equations. The closed form dynamic equation can be derived systematically in many coordinate systems. Let Q1 to Qn be generalized coordinates that completely locate a dynamic system. Let T and U be the total kinetic energy and potential energy stored in the dynamic system. We define the Lagrangian L by L of Qi comma Qi dash is equal to T of Qi comma Qi dash minus U of Qi. Note that the potential energy is a function of generalized coordinates Qi and that the kinetic energy is that of generalized velocities as well as generalized coordinates Qi using in Lagrangian equation of motion of the dynamic system, which is given by d by dt dou L by dou Qi minus dou L by dou Qi, which is equal to capital Qi, where I is equal to 1 to n, where Qi, capital Qi is the generalized force corresponding to the generalized coordinates Qi. Considering the visual work done by non-conservative forces can identify the generalized forces acting on the system. Okay. This is the planar robot dynamic. And before we discussing general robot dynamic in three-dimensional space, we consider the two dog planar robot for which we have derived the equation of motion based on Newton-Euler formulation. The figure shows the same robot mechanism with a few new variables needed for Lagrangian formulation. The exercise is the first robot on the y-axis on that side is the second robot, which the first one is I1M1 and VCL and omega 1 are the parameters. Theta 1 and tau 1 is the first robot parameter, and tau 2 and theta 2, I2 and M2 is the parameters of second robot. This is the 2 degree of freedom robot. DOF is nothing but degree of freedom planar robot. The total kinetic energy stored in the two links moving at linear velocity VC and the angular velocity omega of t at the centroids as shown in the figure is given by t is equal to summation of I is equal to L to 2 into 1 by 2 mi vector of VCT square plus 1 by 2 I1 and omega 1 square, where VCT is represent the magnitude of velocity vector. The linear velocities and the angular velocities are not independent variable, but they are functions of giant angles Angular velocities, that is the generalized coordinates and the generalized velocities that locate the dynamic state of system uniquely. We need to rewrite the above kinetic energy so that it is with respect to theta I and theta dash I. The angular velocities are given by omega 1 is equal to theta 1, omega 2 is equal to theta 1 dash plus theta 2 dash. The linear velocity of the first link is simply VC1 vector of VC1 square is equal to LC1 square theta dash square theta 1 dash square. Sorry. However, the coordinate the centroidal linear velocity of the second link VC2 needs more computation. Treating the centroid C2 as endpoint and applying the formula for the computing the endpoint velocity, field the centroidal velocity, let JC2 be the 2 cross 2 Jacobian matrix relating the centroidal velocity vector to joint velocities. Then the vector VC2 square is equal to GC2 Q dash of square, which is equal to Q dash power T JC2 power T into JC2 Q dash. The coefficients H11 and H2 are the functions of theta 2. The potential energy stored in the two links is given by U is equal to M1 G LC1 sin theta 1 plus M2 G of L1 sin theta 1 plus LC2 sin theta of theta 1 plus theta 2 whole bracket. Now we are ready to obtain the Lagrangian equation of motion by differentiating the above kinetic energy and potential energy for the first joint. Tau L by tau V1 is equal to minus tau L by tau Q1 is equal to minus dou U1 dou U by tau Q1, which is equal to minus where the value of U is given by minus M1 LC1 G cos theta 1 plus M2 G LC2 cos theta plus theta 2 plus L1 C cos theta 1 whole bracket that is equal to minus G1. Now dou L by dou P1 is equal to H11 theta 1 plus H12 theta 2. So differentiating this d by dt dou L by dou Q1 is equal to H11 Q1 plus H12 Q2 plus dou H11 by dou theta 2 into theta 2 dash theta 1 dash plus dou H12 by dou theta 2 dash square. Thus the same equation of motion have been obtained based on Lagrangian formulation. Note that the Lagrangian formulation is simpler and more systematic than the Newton-Euler formulation. The formulate kinetic energy velocities must be obtained, but acceleration are not needed. This acceleration computation is automatically deal with the computation of Lagrangian equation of motion. The difference between the two methods is more significant when the degrees of freedom increases. Since many workless constraint forces and moments are present and the acceleration computation becomes more complex in Newton's Euler formulations. Thank you.